Hello and welcome back. So in this activity we are going to, from a statement in MATLAB, we're going to determine the difference equation, the system function, draw the block diagram, and make a couple of final remarks here. What we have is y equals to filter 0.5 minus 0.8 minus 9, 1, 0.8 x. Remember, this is the input signal, the signal that you want to filter, to be filtered. This is the output of the filter. Okay, and you are filtered the signal with this filter that is characterized. This is the B coefficients, these are the A coefficients. And if you recall, the general difference, this is an IIR filter. MATLAB implements the equation as A of L, Y of M minus L, from L equals 0 to some value, N equals sum of bk x of m minus k, k equals 0 to some value m. This is a difference equation. Effectively, what you have is that the output depends not only on inputs but on previous outputs that have been computed. This enables to significantly reduce the number of coefficients needed to implement a particular frequency response with a fast roll-off, for instance. So what we have here, this y of n is equal, this part is 0.5 x of n minus 0.8 x of n minus 1 minus 9 x of n minus 2. So this is the feed-forward part of the filter, the one that depends on the inputs. If the filter is causal, like in this case, it depends on present and previous inputs, as you see there. And then always you're going to see this 1, which corresponds to the fact that the coefficients, the first AL, the A0 coefficient, the output, A0 here, is equal to 1. Okay? So that's what we have there, that 1. And if we have to put it in the other side of the equation, this positive goes as a minus 0.8 y of n minus 1. Sometimes you see this like this, x of y of n equals minus 0.8 y of n minus 1, the previously computed output, and then everything else, plus 0.5 x of n minus 0.8 x of n minus 1 minus 9 x of n minus 2. So this is the difference equation that we are after. Remember, difference equations in discrete time are the equivalent of differential equations in continuous time. The way you implement frequency selective filters in continuous time are actually by realizing a particular differential equations, and you realize them with resistors, capacitors, inductors. Remember that the current voltage characteristics of capacitors and inductors, right, for a capacitor, C dV dt, this enable us to implement integral differential equations with RLC circuits, or if you need the gains, you could put an operational amplifier. And so, in continuous time, in analog, you will have, if they are active, typically you have an operational amplifier, and then resistors and capacitors, and you can have multiple stages to have faster roll-offs. And what you are implementing is a differential equation. In discrete time, what you have is a difference equation. That's the analog of the differential equation, and what you need are additions, so others, the delay operator, so you need to be able to delay store and multipliers. And so you can implement this in hardware or directly, since these are operations that are in absolutely all processors, from the simplest microcontroller to the processor that you have in any computer, to, of course, a DSP that has been optimized to make these multiply, accumulate operations. So you can do billions, several billions of this per second. Is how you implement these filters. Now, the problem of filter design is how do you design these filter coefficients to achieve the frequency response that you want. So that was the first part. A, determine the difference equation. B, draw the block diagram. Now, the difference equation is a complete characterization of the system, meaning we can find the output and everything that we want to find about the system from the difference equation. An equivalent representation is to look at the block diagram. So we have x of n here, the feed-forward part. You have is multiplied times 0.5. Here you have a delay, c to the minus 1, multiplied times 0.8 minus 0.8. So you have another multiplier. Again, this block can be done in hardware. You can do a particular hardware architecture. You can do this at the transistor level to do a very fast filter, but you don't need to do that because these operations are available in every processor, as I said multiple times. Minus 9. And this, sometimes you denote, you show it like with a single adder. This is that part, or with partial adders, like this. Right? Now, this part we can denote. Now we have to add this other part. So we just got this. So you say, okay, this is added with, we have 1 to get our y of n, and we delay that, c to the minus 1, and this is what we're going to multiply times the minus 0.8. So this is the block diagram of this filter. Now, in general, you could have as many delays as you want here. And this will keep going, right? So we can implement as long as many taps as we need. So that's it, actually. Now, this architecture can be implemented in hardware, it can be implemented in a general purpose CPU, it can be implemented in a microcontroller, it can be implemented in a digital signal processor, that if a CPU has been, the architecture is optimized for the type of operations that you will have in a computer, and that goes from word processing to Excel spreadsheets to symbolic type of operations to search tests to replace tests. Over here, all what we are doing is to make sure that we implement these multipliers, x of n plus some value, the others, and the delays really efficiently, to do several billions of this per second. And that's because that's what you need for filtering, that's what you need for the FFT. It turns out that all this stuff you can implement with the fast Fourier transform. Okay, you can do fast convolution using the fast Fourier transform, as we will see. Now, recall that there are a couple of interconnected things that we have here, right? From the impulse response and that was the output of the system when the input is an impulse, we could go to the frequency, to the system function or the transfer function, right, using the C transform. We can also go and backwards from the inverse transforms. We can also, using the discrete time Fourier transform, we can go to the frequency response. We can go from the discrete time Fourier transform or the frequency response to the system function to the discrete time Fourier transform by evaluating C equals e to the j omega hat, meaning evaluating this is real, this is imaginary, in the C plane around the unit circle. And from the impulse response, we could calculate any output for any other input using convolution. From the system function, we could calculate the output in the C domain as the system function times the Laplace transform of the input. The same thing, the output could be calculated in the frequency domain as the frequency response times the Fourier transform of the input. That's because multiplication in the frequency domain is convolution in the time domain. We could assess from the impulse response causality. We could assess stability. And from the system function also we could do that by looking at the zeros and poles. And this is what we have in the next problem is, okay, do a zero pole plot of this system. Okay? And in MATLAB you just use the function C-plane and you have the C-plane function put the zeros, you put the B coefficients and the A coefficients. So what we will do in this case will be C-plane. What are the B coefficients? From here we can see there are these three, 0.5, 0.8, actually minus 9. Then we have the coefficients 1 and minus 0.8, and that will give us the C-plane. We could also, this will be the zero pole plot, we could also do the frequency response using freqz with the same input, 0.5, minus 0.8, 9, 1, 0.8. This will be with normalized frequency. We can put the how many points, like 2 to the 12.